Hello, and welcome to Expedition Bifrost, exploring new tools in the next frontier. My name is Jonah Friedman. I am the product manager of Bifrost. So first, a quick introduction. What is Bifrost, for anybody who doesn't know? Bifrost is visual programming for 3D graphics, meaning putting together nodes to create visual effects in 3D graphics. We've got some state-of-the-art simulation solvers, including this animation scene here, which is our arrow solver, simulation done by Michael Nielsen. And we've got some non-simulated proceduralism as well. For example, instancing and scattering. We've got a Maya and Arnold integration. And we've got a flexible release schedule with 15 releases and counting. And this release schedule is similar to the Arnold release schedule. So here is our agenda for today. We're going to first talk about Bifrost 2.3, interactive, expressive, and robust. That's going to be how the new features contribute to this. Second, Bifrost 2.3, effective effects, the changes to the effect solvers, and performing on stage, a glimpse of the future. And that's something a little bit more forward-looking. And I won't spoil exactly what that is yet, but there's a hint in the word stage. So first, Bifrost 2.3, and how the new features make Bifrost more interactive, expressive, and robust. So first, interactivity. Almost every parameter is now a virtual slider for fluid interactive control. So you can just click on the name of any port and drag to change the value. This is an exponential slider, meaning it works on both small values, like the width of a strand, or very large values, like a temperature. It'll adjust it the right amount. Got nice interaction with vectors and colors. So sliding a vector is the same thing as scaling that vector. F-curves are fully interactive, which is very important, especially in cases like this, where the relationship that you're controlling with your F-curve may be a little bit abstract. And our sliders respect Maya muscle memory. They've taken a lot of inspiration from the channel box, and both middle click, dragging, and modifier keys are preserved from there. There's a couple pieces of underlying technology that have enabled this. First, dynamic constants, which allows us to change values without needing to recompile, and feedback port preservation, which allows us to edit live simulations. So let's take a look at that. Here I've got a particle simulation that's kind of like a flocking type simulation going around these characters. And I'm going to change the instancing to instance a fish here instead. So now I've got my shark model attached there, and I can continue playing the simulation from where it was. I can also do things like adjust the scale and build any graph after the simulation that I want. What I'm going to do now is write out this particular frame of my simulation and then use that as my initial state of my simulation. So I'm setting that up, now detaching my emitter, and now I've got a simulation that starts from that middle frame. And I was able to do that very fluidly and very easily. So the Bifrost graph is now more expressive as well. One way in which we've done this is with auto ports with defaults. And to explain what this is, it was previously impossible to publish a compound with an auto port that had a default value. And by lifting this limitation, it means that it's possible to override a simple value, like 1.5, with something else, like a field. And this is more expressive for compound authors to start with. Because they can now create systems of nodes that are designed to be plugged into each other in very fluid ways with override kind of behaviors. And Costa will talk about this more, but for example, in simulation, many float ports can be overridden by a field. And on NPM sources, there's something called firmness, and instead of setting the firmness with a value like 1.5, it can be overridden by a field that varies those values in space. Also, user graphs are more expressive, because a graph that is set up this simply with a field plugged into a port is much more readable and less verbose. And that makes a graph more expressive to me. Also in the more expressive category, terminals. Last time I showed them to you, terminals were in beta, and they are now officially out of beta. We also now allow terminals in loops, and this is really what makes the terminals more expressive than they were before. So I can put a compound containing a terminal into a loop, and it creates a renderable geometry for each iteration of that loop. In this example, I have an iterative displace points. So every time this loop goes through, it displaces my geometry a bit. And what I've done here is I've put a diagnostic node into that loop that draws an arrow for the displacement. And so when I turn on the diagnostic flag, I can see all of those stacked arrows seeing how the displacement changed throughout the loop. And Bifrost is now a more robust tool as well. The first way I'd like to highlight this is with our Maya integration. We fixed several critical issues with it. First, there are some evaluation fixes. The dreaded value not set on job bug is fixed, which a lot of people have hit, especially people doing rigging with Bifrost. And this was so important that we did a patch release for it as well. So if you're using Bifrost 2.2 in production and want to use like a small upgrade, that's available for you. That's Bifrost 2212. There's also a Bifrost 2213 now, which fixed a different issue. But those patch releases are tiny changes and safe upgrades. Other fixes, we have fixed some key issues with instances in the viewport, and bringing meshes into the graph is now significantly faster, especially when those meshes have color sets. So that will help people as well. And another feature to highlight in the robustness category are unknown nodes. So if a graph relies on some reference assets that you don't have, you now get an unknown node and your graph is fixable. And it's the same thing with ports. On the top you can see an unknown port, and on the bottom we can see some unknown nodes. And these unknown nodes are actually even more important than this. For one thing, unknown nodes actually represent an overhaul of all of our asset loading. So they really contribute to Bifrost loading quickly. Bifrost as a whole now loads in 2 seconds, and this also has some implications for rendering, especially on render farms. They also have made our dependencies more robust. Compound packs tend to contain building blocks and then high-level compounds that use those. So that's a dependency. The high-level compound uses the building block. And these dependencies are now much simpler, and they no longer depend on file names. And this allows us to merge all of our compound files together for distribution as well, and package them up for releases. And authors of compound packs can do this as well. So with that, I'm going to give it over to Costa for Bifrost 2.3, Effective Effects.
Thank you, Jonah. With that, we can now move on to the Effective Effects section, where I will take you through what changes this release of Bifrost brings to the effects component, which make working with effects, well, more effective. But first, who am I? My name is Konstantinos Stamatelos, also known as Costa. I'm responsible for driving and designing the effects features in Bifrost, such as the aero and combustion systems, particle simulation system, and the NPM simulation system, along with volume tools. The most significant new feature I'm excited to present is new functionality which easily and directly allows varying the initial conditions for any given simulation. Injecting spatial variations at sourcing time over the values of the physical properties which make up any simulation is crucial for achieving natural and dynamic behavior, as rarely are things ever so homogeneous in nature. This is now achievable and much more artistically directable using the system of fields introduced in the last version of Bifrost by mapping field values directly into simulation property ports. This leverages the technology of the auto port with the default values Jonah introduced earlier. Let's now have a look at this in action. Previous versions of Bifrost already provided a solution for varying source properties. If we look at this particle simulation, let's say I wanted to vary the size of the points so that they're not all the same. What I would have to do in earlier version is get this vary source property node here, and then manually input the name of the property which I want to vary. And here I'm just going to input the name size, and then I would actually have to plug this node in between my input mesh and the sourcing of the particles, which is a little bit clunky and cumbersome. And so if I play back now, I see that I have a variation. The new way of doing things leverages the system of generic fields, and this allows you to directly control the variation by plugging fields in the properties themselves on the source particle node. So in this case, I'm going to do the same thing except using fields. So I'm just going to expand this particle properties port here. And then where I have size, this port here, although it is a float port that has a default value of 0.1, it's also able to change to accommodate an input of a field. So if I search, for example, for a fractal noise field, I can then plug that directly into the size, and then if I rewind, I see that I have a variation. In this case, it's a little bit too intense, so I'm just going to decrease the magnitude to 0.25. And here we go. The reason why I have some black particles is because the fractal noise field also includes negative values, and so I could easily rectify that by getting an absolute value node, plugging that in, and then piping that directly into the size. And what I really love about this is that it's very easy to understand when looking at a graph that I have a fractal noise field that's plugged directly into the size port of my source particles, so I'm not stuck looking in chains of various source particle nodes to see which ones are controlling what. And obviously we have all of the parameters that exist on the fractal noise field, for example, to customize the very nature of the variation. If we look at frequency, at a frequency of 0.5, we have somewhat of an even spread of particle sizes, whereas if I start decreasing that frequency, I'm going to get some chunkier distributions. And of course, this fractal noise field can be plugged into any other port where this is applicable. So if I take this field now and let's say I plug it into the speed, I can see that it's applying itself there too. However, the magnitude of this field that I'm using to vary the size is actually not enough for speed. But if I do want the variation to be the same so that bigger particles move faster, then I can just use a multiplier here to increase the magnitude of the fractal noise field without having to get a second one. So I'll just plug this here, and then I'll get a scalar field. And I'll say, okay, maybe I want to multiply it by 5. And I'll plug the result of that into the speed. And now I have big particles that move fast and small particles that move slow. And if I reorganize my graph and take a step back, once again, I could clearly see that I have this fractal noise field and that it's affecting size and speed with a little bit of mathematical influence along the way. Although I've been using a particle simulation system to demonstrate this new functionality up to now, it's available across all the simulation systems and supported on relevant ports of almost all the simulation compounds, with certain exceptions which are still a work in progress. For NPM Granular, this allows going from an otherwise unexciting melting snowman to a much more natural and artistically controlled version by directly affecting specific physical properties using field arrangements. Similarly, captivating results can be achieved for this crumbling sandcastle. For aerodynamic simulations, the simple sphere is a notoriously bad source, as it produces the dreaded mushroom shapes and an overall unattractive aesthetic, especially in the absence of any force or influence as seen here. But with just a couple of field connections to properties like fog density, initial velocity, and temperature, it's easy to get much more dynamic and natural looking results. While this new way to vary initial conditions for simulations is the biggest new feature for effects in Bifrost 2.3, there are a few more exciting new things to mention, and since we're looking at aero, I'd like to show you some improvements to the post-aero refinement or up-resing process. For example, if we look at this fairly involving aero graph which has a whole bunch of input data and we want to up-res that, what you would have had to do before is, still using the same node, which is the post-refine aero node, you would have had to plug in every single source, every collider, every influence, and so on and so forth. So what we've done for this version is consolidated all of this simulation input data, and now you can pipe that out from this new port on the simulate arrow, which is called solver inputs. So all you have to do to upres is just connect your original arrow volume, connect your solver inputs, and then just output that. What's more, both the arrow volume and the solver input data can be cached out to disk. And once that's complete, you can perform a post-simulation refinement or upresing directly from files on disk without ever requiring the original scene or the original graph, which is pretty awesome. Finally, a few other noteworthy effects changes in this release include general stability and performance improvements for MPM cloth, along with revised behavior for constrained cloth, which is also subject to collisions, and newly animatable properties on the cloth node for doing things like inflating and popping. For volumes, streamlined adaptivity now brings the benefits of adaptive volumes to the voxelization of simulation sources and colliders, and also easily enables the conversion of a regular VDB volume to an adaptive Bifrost volume, with enhancements also reaching the interactivity of the viewport for displaying these volumes. And of course, the usual slew of relevant bug and stability performance fixes also await you in Bifrost 2.3. This brings me to the end of the Effective Effects update, and I will now hand it over to Guillaume, who will take you through what the future holds for Bifrost.
Thank you, Costa. This is Performing on Stage, a glimpse of the future. My name is Guillaume Laforge, and I'm a development manager in the Bifrost team. Today, I'm going to present something we are working on. With USD adoption across our industry, Bifrost Visual Programming Language will fit very well in such ecosystem. That's why we are working on some building blocks, some Bifrost nodes that allow you to manipulate USD objects like stage, layer, prims, or variant. From those low-level nodes, we can construct some compounds using Bifrost Visual Programming System that can create USD mesh from Bifrost geometry or vice versa, or transform prims, create variants, creating layers for specific scenarios, like in this little example, where we are going to follow the life of a model across departments in a studio. Thanks to Apple and to the AR Quick Look web page, in this example, we follow the journey of this downloaded asset, that is the toy biplane. So we create in Bifrost, using Bifrost USD node, we will create some layers first. So the first layer will be our asset layer, and then we'll insert a modeling sub-layer. In the Maya USD layer editor, you can see that we can visualize the layers. And what we are going to do is to work on the modeling, because the modeling department will put all its data on it. So we are targeting this layer. We will author it. From this layer, we can add a USD prim in it. And this prim right now is displaying nothing in the viewport, but we can reference or payload something on disk, like the USDZ asset from the Apple website. And so we can unload or load our asset using Maya USD capabilities to load on demand a USD payload, and then we can reference. For the reference, we took the plane and just ran a polygon reduction on it. So now we've got a proxy and a render plane. Our model is ready for the next department. In the next department, we are going to add a simulation to add an effect on our plane. So loading the model version 1 as a start, this compound will load the layer and will automatically increment it to version 2. So the FX department won't override the layer. So the FX department is going to work in this little compound called add FX layer, where a new USD layer is created, and as a sublayer, We also set the stage timecode, and then we create a variant set called type. This variant set will allow to create two variants, one that is called classic, and the classic variant is just doing nothing, basically. It's the original model, and then there's the flag variant. The flag variant will be where the FX team will work. He will add, so we can see in the outliner there are now two variants in the USD stage, but they are empty for now. And using an NPM cloth simulations that we are currently displaying, so here it's a Bifrost geometry in the viewport, it's not a USD geometry. So we can do our work in this compound, it's classic Bifrost simulation work, and then we can inject this geometry in the USD stage. So if we switch to the variant flag, we can now see the USD flag. And we also we created the USD material, we assign it to the flag. So that's it for the FX work. We can save our layer or our model version 2 now and go to the next department. That is the look development department. Here again, we are just loading our layer coming from the FX department. And in order to work in isolation in our little sandbox for the look development team, we create a new layer. So if you turn off the FX, you can see your model without FX. Here we got a look variant set, and we create two variants. One is default, and the other one will be new colors. The new colors will add a new variant overriding the texture path of the diffuse color of our shader. So now we got two variant sets, and we can combine them, like taking the new colors variant of the look and taking the classic type for the type variant set. So from a simple asset, now we can have a multiple combination of multiple variation, and we will use those variation in the layout department. In the layout department, we are going to instantiate our plane using a USD point instancer. Bifrost USD nodes allow you to create a USD point instancer very easily. So first, we create a new layer that we are not loading the asset directly. We create a short layer. In this short layer, we create a sublayer called layout, and the layout team will work in this layer. But before injecting data in the layer, we create some Bifrost points that we are scattering. In this example, it's very simple, just a little grid. And those points are passed to the USD instancer and will allow our asset to be instantiated. But our asset will variate. So on each point, we will pick randomly different variant. That's why in the viewport, you can see we have some plane with the new colors, others with the flag coming from FX. So using Bifrost visual programming language, you can really control how you are scattering your instances. The timing also of the animation is controlled, is modified per instance. In this example, you can really control how to assign shaders. Here we control based on the name of the mesh, and we have multiple rules. We could also control based on the local height of the mesh. So here we ask the USD point position of the mesh, and if it's higher than a specific threshold or lower, we assign the mesh. And finally here we are assigned by color. If there's an attribute in the USD mesh, a diffuse color attribute that is matching our color, we assign. To conclude this presentation, we are going to take a look at a little bit more involved instancing system using the Bifrost scattering tools that are actually very easy to port to USD. So here it's a native Bifrost geometry in the viewport. There's no USD in the tree scatterer nodes, but we can output the data to a USD stage. So as soon as you connect to the output, a Maya USD stage is created, and you can visualize the USD data directly in the viewport. So here we modify in Bifrost. The Bifrost instancer is modified and is translated to USD point instancer on the fly. And this is concluding my presentation. Thank you so much for watching.